nada más. Y ya empezó igual el streaming en YouTube, entonces ya mismo podemos empezar.
Buenísimo. All right. Well, thank you very much for the invitation. I'm Bernardo Campo. I'm the president of ARDI. ARDI is a company that we started with Juan Sebastian. So thank you for the invitation, Juanse. And yeah, we're going to go and we're going to talk about advances in biochar production. Mateo Davalos is going to talk about the engineering side, and I'm going to be talking about the biochar. Well, this is, well, just to show you guys, we started 8 years ago, grad students from Iowa State, and we decided to start making machines, start making biochar, and therefore start making machines for biochar production. And we're all from the same lab, the thermochemical conversion lab, pyrolysis lab in Iowa State. So there are many take-home messages today, but if there's something that I want you guys to understand is, I want you to understand a little bit what is biochar. You know, people talk about charcoal, biochar, and some other carbon products. I want you to understand the benefits of biochar in soils, the benefits in the environment, how it's made, the generality, you know, how you make a good char, because there are many carbon products again. And then we're going to be talking about some technical parameters. Not all the biochars are the same, not at all. In fact, that's one of the problems that we have in our industry is in terms of you know, how we classify the carbons, how we use it correctly. And Mateo is going to be talking about engineering production, biochar production, and here is where we, you know, we try to make an impact in the biochar industry by making our machines how Mateo is going to show you guys. Let me see if I can move this around. Okay. So what is biochar? Biochar is a charcoal-like material. Okay, here on the right you see this is a charcoal piece. What it's charcoal-like material because it looks black and it looks the same as charcoal. But in general, we make them at higher temperatures than the regular charcoals. That's the number one thing. The other thing, there's many processes to make biochar, and they give different qualities on the biochar. Okay, but biochar per se, it's a charcoal-like material. It looks like charcoal. Some of the charcoals actually could be classified as biochar. There are some parameters that we need to, that IBI, the International Biochar Initiative, recommends to follow. And those one, for example, is the H2C ratio, the hydrogen to carbon ratio. That will tell you, you know, how stringent the pyrolysis system was and how aromatic the component is. You know, starting from a very low H2C ratio, from a very high H2C ratio in the biochar. As you start cooking it and getting stringent conditions, you're making it slower. So the IBI recommends around 0.7 or lower. With that, the carbon will stay in the environment for many, many years. So it's a biochar-like material. This has been developed, the biochar industry started to develop roughly 20 years ago. And as you see in this chart, what I'm showing you is the scientific publications on this. So it has been growing every year since the development of this. And I'm going to tell you a little bit how it was found, this biochar, and how this concept has developed from the beginning. And the patents, right? There's patents and things are being developed. So the industry is moving. I wish it would be moving much faster than what it is now, but we're going to be talking some of the challenges that we have and how we are addressing those challenges and trying to develop the industry better. So these are some of the pictures, some of the trials. A few of them I've been involved, a few of them. These are just some pictures just for you to know, right? But there are biochar trials all over the world. And again, there's lots of charcoals, there's lots of soils. If you go in the right side, in the middle right side corner, there's a picture of a kid with a corn. That picture has resonated in the IBI. On the right of that picture, we have the terra preta soils made by Indians making this charcoal. And after 6,000 years of those soils being made, we go now and we can check, we can carbon date, and we see the benefits of those soils in the Amazonian soils, which, by the way, they're very poor, they're very acidic, okay? But these Indians made these soils and they're extremely good soils, like what you see in those pictures. What biochar does for the soil? A lot of things. First of all, you increase organic carbon or organic matter in the soil. That is huge, okay? So you have the mineral phase and organic matter, and this is 100% organic matter, put it in general terms. We improve the cation exchange capacity very significantly, and ion exchange capacity as well, a little bit. The water retention, good soils retain a lot of water, and not just retain a lot of water, but that water is usable by the plants, okay? So those are the things that they're very important, As you retain cations and nutrients, guess what? All the microbes can grow. And now you have a healthy soil full of microbes. The carbon also, a very important thing is, besides these chemical properties that I've been talking, it improves the aggregations in soil. So what it does is it binds with the clay particles and the soil particles and makes small aggregates. And then the roots can grow better. The roots can reach further down. There's more oxygen in those soils. So literally it changes the nature of the soil, okay? Like that, the picture that I was just referring, you grab a soil that has less than 1% of organic matter, and then you go to the right and you have a soil that has probably 5% organic matter. I don't know the numbers, but keep the concept. So you definitely change the soil very significantly. And when you change the soil, the plants and the microbes and the biota that it lives in that soil changes enormously. Well, on the soil, we change the soil. On the environment, the biochar, I mean, we're super excited on the biochar, basically, or most importantly, for the carbon sequestration. If there is a technology that we need to focus as in the scientific community to sequester carbon dioxide, I think it's biochar. Not because I work on this, but the benefits of this. You improve the soil and you make a carbon that the microbes or the ambient factors cannot break it down for hundreds to thousands of years. Depends on how you do it. Again, depends on don't call it quality, but on the properties of the biochar. But hundreds to thousands of years. So what you're doing is you're grabbing waste material, you're pyrolyzing, carbonizing it in some way. You're making this charcoal, you use it for soils, you improve the soil health in 20 different factors. And you're sequestering carbon as you do that. And not a little bit amount of carbon, a lot of carbon dioxide, okay? I'll talk a little bit on that. And then other things is, as you improve the water retention, guess what? You reduce erosion. As you improve the aggregations in the soil, you have more infiltration, you have less erosion. As you improve the cation exchange capacity, and in some cases an ion, you retain more nutrients. The microbes retain a lot more nutrients because they're growing and they're eating all those nutrients. And guess what? You reduce the leaching of those nutrients from those soils. You prevent contamination. And there's plenty of scientific articles about this. On the crop yield, again, you improve the soil. If a soil is very good, guess what? You're not going to improve it that much. But in most cases, the soils are not very good, and you can improve very significantly the soil. And you increase the soil productivity, the plants, the biomass, and the yields. And there's plenty of that. A colleague of mine, David Laird, he did this research ago, several years ago, 10 years ago. But it's just to show you the impact of this in numbers. His research was done with 500 days, and he put some biochar in the soil. He put 0 non-biochar and 20 grams of biochar per kilogram of soil, which 20 grams is 2%, is quite a bit of char. But those are the numbers that we want to include and make significant changes in the soil, okay? Well, but if you see there, the initial organic carbon was, let's call it 2%, 20 grams. And then he moved it from 2 to 3.4, okay? He added more than 50% of carbon. The nitrogen also increased, probably because of the nitrogen retention, and also the microbes and all the other things. Cation exchange capacity, it increased 10%. The bulk density, this is how compacted, well, it's related to how compacted or how heavy that soil is, right? And you decrease it. Now it's a better soil, it's tilt, it's easy to work. The roots can go through. And the same, decrease roughly 10%. And the pH in this soil is a little acidic, just a little bit. And he increased the pH from 6.3 to 7.2, which is a substantial increase. Again, in this soil, it's good to increase the pH. In other soils, it's not, and you need to use a different type of biochar, okay? But you will see some of the, like in this case here, I'm showing you This is a meta-analysis where what they do is they grab all sorts of researchers and scientific publications, and they analyze the impact of biochar in the soils, okay? And they see that some crops, they do extremely well, and this is the increase in productivity, 30% or 60%. They increase a lot. And some others, they don't. And or these situations, they didn't, okay, or like in this case. But on average, this is the problem of meta-analysis. What we need to do is understand, first of all, they're understanding the material here and the conditions that they're using it. So what I'm saying is, if we know the soils and we know the plants, we should be able to always increase the yield, okay? But again, we're trying this. But on average, in all these analyses that they've done, all the scientific publications that they gather for this meta-analysis, there's a substantial increase. I think it was on average 10, 20%, okay? So it can increase the yield, yes. In most scenarios, you will increase the yield of the crop. And this is, many people ask me, well, how we are sequestering how the biochar sequesters CO2? Actually, it's not really the biochar that sequesters CO2. And if you don't mind, I'm gonna put my sweater now because it's starting to get a little cold. So how does biochar sequester CO2? And it's basically not the biochar, but the plant. The plant is growing. Okay, here on the left, for example, this is a normal scenario. This tree is growing, it's sequestering CO2 from the atmosphere, it's building his biomass, and then when it dies, the microbes will break that biomass down, and it will create CO2, and it will go up to the environment, right? So it will be a cycle. So we grow trees, and we'll get to the point we're sequestering the trees, but we'll get to the point that it will be carbon neutral because it won't sequester more. Okay, now on the right side, what we're trying to explain here is that as we produce the biochar, the CO2 was fixed by the plant, but the pyrolysis method locks the carbon into a form that it doesn't break down. Okay, and that is, I would say, the most outstanding of all the factors that we just said of the biochar is the carbon sequestration. So we make the biochar, and roughly in the process, this is from another company, it's called Biochar Solutions. But from that carbon, roughly 50% is stored in the biochar. And again, depends on the method and how you do it, but just to get general numbers. And then the other half of the carbon, it's in the syngas or the bio that is used in the process. Like in our process, and most of them are self-sustained. So we use the same energy, okay? And again, you start making biochar, and every year, as you pyrolyze more and more biomass, you create more biochar, and all that biochar goes into the soil, and you're building the carbon in the soil. So what you're doing is all that geological forms of carbon, like petroleum and coal, it's been burnt, goes through the air. Then the plant sequesters it, and the biochar locks it, and then goes back into the soil. Okay, that is, I would say, the most important of all the factors that we just said. Okay, and this is some of the respirations. It's just more fun than anything else because how a researcher is going to demonstrate that the biochar stays there for 100 years or 1,000 years, right? So what we do incubations, we show that, but the most important of all these testimonies is going and measuring the soil. We grab the soil and we carbon date that soil, okay? And as the same as the Amazonian soils that I was talking before, in the molly soils, the soils that we have here in Iowa, those ones, we pick a soil particle and we can tell when that carbon was made. It's just fascinating. And guess what? Roughly 40% of the carbon that we have in our soils come from pyrogenic origin. It means fires made that carbon, okay? And that is all due to the lightning, that thousands of years ago has been burning the prairies here, and the Indians that were burning the prairies, so the buffaloes will come and eat. Over time, that accumulation of organic carbon made the organic matter that we have now, and made these soils that they're 6 to 10 feet in depth with an outstanding chemical, biological, and physical properties. And that's why we get corns here with 200 or 250 bushels an acre, okay? Because the soil is just amazing. So here in this chart here, what I wanted to show you is a little bit of addition of biochar, a little bit, like 1% of biochar. It will require roughly 19 tons of biochar per hectare, which is a lot, okay? But you're gonna be sequestering with this biochar was corn store biochar, roughly 36 tons of CO2, okay? The biochar that we do here in RD, roughly our carbon footprint is, it's for every ton of biochar that we make, we're sequestering 3 tons of CO2, okay? But this is just another biochar and another example that we did in the past, okay? All right, now more for the gardeners there in the presentation. So like anything, we need to know the circumstances where we are applying this biochar and match it, right? So this is kind of a little bit of a act of caution for those researchers like us. So you need to understand the environment, you need to understand the plant, you need to understand the soil, and then you're gonna make the appropriate biochar for those soils, okay? No, it's not just making a biochar and just applying it. Why I'm saying that? For example, what I was telling you before, the soil that my colleague was using was 6 of pH, okay? Imagine if you put an acidic biochar in those situations, which you can do, by the way. It's more difficult, much more difficult. Well, you would acidify a little bit more the soil, okay? In general, it's the opposite. We got very alkaline soils, and we come up, and a researcher goes and put a very high pH biochar, and guess what he finds out? That biochar doesn't work, right? Well, it's a little bit more complicated. My point is we need to understand what we have and how we're going to use it. That's the most important thing, okay? All right, another take-home message, okay? And by the way, there's going to be a quiz at the end of this, so hopefully you're taking notes. You got different processes to make biochars, and guess what? It makes different carbons. You get different feedstocks, and that makes different carbons. You have different operating conditions, and that makes different carbons. So it's a lot more tricky. It's not just carbonizing. Here on the left, what I want you to show you is how how the biochar resonate in some people, and they think it's charcoal making, okay? And that's the thing we need to separate ourselves. We want an industrial system that make, without pollution, a good quality material, and the material that we know. The charcoal making, yeah, it's a batch system. It's like a incomplete combustion, but it's not controlled, so you don't know what you're making. Well, in the generality, okay? And here the picture on the bottom, okay, you can see the different types of what people call biochar, okay? And this is from a university, a picture from a university. But it's just for you guys to get a sense of that the biochar is black, but we need to understand a lot more than that, okay? It's like on the left, we have coffee there being torrefied at different temperatures, right? The same thing with the materials, okay? And on the bottom right corner, we have the Iowa State facility that we have a gasifier and a paralyzer. The same thing to make different materials and understand more the process. On the upper picture there, this is a Pyreg, it's another company from Germany. There's a gasification, I think this is ICM. But anyway, there are different companies making all these machines, all right? And well, there are different biochar products out there, okay? And my point to you guys is, remember, biochar is carbon. You're gonna put it in the soil. Well, the plant needs a lot more than carbon. Actually, in some way, the carbon is, the plant doesn't feed carbon, right? Doesn't feed from carbon. So the biochar is like a sponge that holds all the water and nutrients and microbes. It holds all these microbes in it. So that's what to keep in mind. And we have different products in the market. And all these products, like I'm showing you there, there's a few of them. They're pretty expensive. And that's one of the things that we are trying to work, is how to scale it up, make it a more effective, a better biochar, put it in those ways, that we know what it is, and make it cheaper so people can use it more, and we can sequester more carbon, okay? But all these are great products, but again, they're too expensive. So with our machines, we make biochar. We sell all sorts of formulations of biochar. In our case, we try to sell biochar to people that know how to use biochar. Otherwise, we mix it with compost, or we mix it with worm casting, okay? so people can use it right away. Okay, so here I'm showing you some solid materials. We sell super sacks and blah blah blah. This is worm casting, the same. You get all the nutrients, all the microbes, and then you put the biochar in it. And these are some liquid formulations that what we do is we grind extremely fine that biochar sustains suspension, and then you can include it into your irrigation system, and you can be adding those nutrients with the biochar locking those nutrients. This is some compost and some biochars. But it's just to show you guys that we need to, as an industry, we need to look into biochar products, not selling biochar. Okay. Engineering biochar. All right. Mateo, hope you're ready for that. We're 20 minutes. I'm getting closer to my friend, so I want to make sure I don't exceed my time. That it's one of my challenges always. So to make biochar, and again, biochar is a kind of a loose term. There's many things considered as biochar. Okay, the IBI has some classification of that, and then there's another institution in Europe, European biochar. I can't remember. The European biochar certificate. Well, they try to define the biochar in some way, and they're a little bit more stringent in what you can call biochar. Okay. Basically, there are different pyrolysis thermochemical systems. Okay, one of them is torrefaction, which you could make biochar at higher temperatures, carbonization, slow pyrolysis, fast pyrolysis, and gasification. Okay, this is mostly the ones that people make biochar with. There's another one that I didn't put here because it's more in the research. It's hydrothermal liquefaction, and that's done with water or solvents sometimes at very high pressures and temperatures. But for example, it's just to show how different methods can make biochar. But imagine this: when we're using torrefaction, we're using 300 degrees Celsius, and we're using 10 hours or 20 hours of cooking, right? It's very slow rate of heat. Then carbonization, we get a roughly 400, 400 degrees Celsius in hours, sometimes days. This is what I refer to the old, the picture with the old charcoal making system. Slow pyrolysis, which is very slow, similar, typically goes anywhere from 400 to 600, but it takes hours. Fast pyrolysis, that's something that I'm going to spend a few minutes later. And we heat up the biomass very, very fast. So we need very small particles to heat it up really, really quickly. And the intention of that is not to make biochar, or the primarily intention of that is not to make biochar, is to make bioil. And we also make some biochar. Okay, but it takes seconds, the reaction. And gasification, the same, similar thing, is minutes to hours. But the idea with the gasification is you get combustible gases, right? So you put some air, not too much, enough to have all this breakage of the biomass and turn all this into gases, okay? And then you can make some biochar, or you can make some ash if you continue to the combustion towards a full complete combustion. But what I'm trying to say from this slide is we have different methods for making biochar, and therefore the biochars are going to be very different, and we need to know the properties so we can use it correctly. All right, talking about fast pyrolysis, right? And fast pyrolysis, we process everything in seconds, like a fluidized bed, roughly 2 to 10 seconds, for example. Okay, in RD, we don't do fast pyrolysis, we do intermediate. It's not even, it's not even slow like in hours. We do it roughly 15 minutes, 30 minutes, somewhere around there. Depends on the conditions that we want to do. But here we cook the material very, very fast, a few seconds. So from the left, we have any biomass, and biomass is again very broad term. Here we have some stover. But we are using wood chips in our facility. We use rice hulls. We use oat hulls. We use anything. We have been pyrolyzing bones. We have been pyrolyzing chicken litter, the poop from the chickens, because it's still in the bed. There's quite a bit of carbon and energy. If there's carbon, roughly, and energy, we can pyrolyze. That's what I like to say, just to simplify the concept. But we pyrolyze it. Here's a picture in the middle, and from the pyrolysis. This is fast pyrolysis. We're going to get gases, roughly, let's say 10, 20%. We're going to get bioil, which is going to be most of the product. will be from 40 to 70%, depends on how you do it and what materials you're using, and etc. And you're going to make biochar, right? But again, it's going to be 10% of the yield. It's not going to be much, maybe 30% in some cases. All right, and now we're bringing to the point of, okay, we understand how we make the biochar. Now we're going to get biochars from all sorts of different compositions. And how do we classify them? How we understand them? How we correctly use this material in this scenario or this other scenario? So we do lots of analysis: chemical analysis, proximate analysis, elemental analysis, the calorimeters, ICPs, FTIRs, NMRs, all sorts of chemical characterizations, so we understand the physical, okay, the particle size, right, the density, the true density of the particles, Another thing that I'm gonna stop a little bit, and in the next slides I'm gonna talk a few minutes, is the surface area, okay, and the porosity, because as I said in the past, the biochar, generally speaking, has a lot of pores, and in those pores the microbes reside, and in those pores you absorb a lot of chemical components. So people refer as porosity as surface area because they want to see more pores, and therefore they will refer as more pores is a better biochar. Well, yes and no, okay, but it's something to keep in mind. And people refer to see that as a BET surface area, okay, and that's something that I'm going to address in a little bit. But I will discourage my scientific colleagues to spend too much time in surface area, because it's just an indicator of the surface, and the pores that we're typically measuring with this surface area in general are very, very small, that they're not the, like the sauce in the biochar, they're not, okay? But we're gonna address it in a little bit. And transportation, there are lots of things that we do for transportation and make sure that we're safe in how we do it. So respiration, or we understand and study the half-mean life of these biochars, and we do all sorts of analysis for those. All right, going back to the concept that biochars is not just black charcoal. Okay, this is just to go in a little bit more into the chemical composition. Yes, you're making aromatic rings that are very stable. All those aromatic rings are very hard for the microbes to break, and the bigger and the more the bigger the structure of these rings, the more difficult for the microbes to break down. But it's not just that. You have here it's represented on this side, but it's in many other places. You have functional groups. You get all sorts of other elements: carbon, oxygen, nitrogen, sulfur, all sorts of other metalloids that you have within the biochar, and those create some chemisorption properties, or could be some chemical reactions as well. And the point is, they have a lot more call it reactivity, but they interact a lot more with the soil and with the microbes and with everything else. So it's a lot more complicated than that, okay? In the right, just to show exactly that, this is an experiment that I used to do in Iowa State, where we have a Kool-Aid. It's just a drink for kids with different pigments, different colors. And then you filter through the different charcoals, and then you get all these different colors, because some of those chemicals are being absorbed with one biochar, but not with the other one. Okay, it's just to show that they're all black, they look the same, but chemically they're very different. All right, and those are the things we need to understand more and more. And here on the bottom we have a chart which is the pyrolysis temperature, and the pyrolysis temperature here goes anywhere from 200 roughly to 800, or I've seen even much higher. And here you have the yield of the biochar. From 100 you get to 20, 10%. That's something to keep in mind, because you change the composition, but you change your mass balance very significantly, and your economics very significantly. So there's always sweet spots, okay? With that, you also change for example, the index that I was referring in the past, the hydrogen to carbon ratio or oxygen to carbon ratio, they relate very well. You change those, and those also change the half-mean life of that biochar in soils, okay? So that's why things get a little bit more tricky. But in general, if we do it like we're supposed to do, biochars will stay in the soil for hundreds of years, maybe thousands, all right? That is the most important concept I want you resonate in you guys. This is another chart from Johannes Lehmann, one of the greatest researchers in biochar. And the whole point of this is showing how different the properties are. Here is pH in red. This is cation exchange capacity. This is carbon recovery. This is surface area. And all those just by changing the temperature. Look at the span of responses that we're having. So the point of this is temperature is one of the most important factors to change the biochar, yield and properties, okay? And again, there's a lot of tweaking. And in the industrial world, we understand this so we can make a better biochar for those specific situations, okay? Surface area, what I was referring before, if you see this charcoal here, you start seeing all these pores, which is, one of the, I would say, one of the greatest attributes from these biochars, okay, that it holds a lot of moisture. All right, so people like that concept, and I think it's a wonderful thing to develop, but we refer as surface area. If you add more pores, you're gonna measure more surface area. And as you see here, we got all these temperatures in this chart, and you got surface area going higher around 500 or 800, and all these are from all sorts of different feedstocks. But again, it's not just temperature. You have all these biochars at 500, 600 that they don't have any surface area, less than 100. And you have all these that have up to 500. You have a few of them that are more than 500, okay? But again, careful with this, because the surface area you're measuring the very fine pores, which is mostly what you're measuring. And there's some mesopores and macropores that in general are those that we're trying to, I don't know, we refer those as the good pores, okay? It's not like that, but anyway. My point is surface area, for me, is just an index, okay? It doesn't mean much in our management. Excellent, so we talk a little bit about the soil, the benefits of biochar, the soil, the environment, a little bit of the chemical composition. We talk a little bit about reactors, or the process. Now we're gonna be talking a little bit about the different equipment that we use for making biochar. Excellent. So this is low technology pyrolyzers, okay? And it doesn't mean that they're bad or they make a bad char, not at all. What we're trying to say here is like, well, they're very low investment in making them. Here is a retort, another retort. This is the TLAD. There are different systems to make biochar. In many of these cases, the biochar is a second product. So this one, for example, is used for heat, and whatever you have left is the biochar, okay? So they're not bad, but what we're trying to say is we need an industrial system to actually get the biochar that you want, right? It's not just the excess material, the leftover, the co-product, not at all. We need the reactor to make the biochar that we want. And in this system, they're more difficult, okay? And the batch systems, we feel this is what we did in Nicaragua, very similar. You put material in here, and then the gases that are produced, they cook the reactor and so forth, But it takes a lot of time. And also, it's very hard with the moisture to control the temperature of the different batches, for example. Okay, so again, low technology pyrolyzers. Other low technology pyrolyzers, which these ones are the one that we maybe we're more familiar with, right? In the right, we have a pit in the ground, and then we put all the material, we start the fire, and then we cover it, and we suffocate the fire, and we let it, carbonize over time. Generally takes a day or a couple of days. On the left, the same, this is another structure, but it's a metal structure, but it's a similar way. We just load it up, we ignite it with propane or something else, and once it gets to the temperature, it continues going, and then we add a little bit of air here and there to maintain the temperature. But as you see, it's very polluting. We have a lot of smoke, plus the controlling of this is quite a bit of a science. So it's not so simple to make the biochar that we want. That's the take-home message. Excellent. And here, what I'm showing you guys is, some of the reactors in Iowa State that they were using for making biochar, bio-oil, or any product. And as you see, all of these are great research equipment, but they make very little. They're very expensive. They have a lot of sensors and automation because they are for research, right? But this is what we need to develop the concepts. And then we need the industrial world to come in and develop these reactors. And here, this is just a few reactors. They're pretty old, all of them. But the idea is there are some industrial reactors. There are. This is my opinion, but in general, what we're facing is very expensive reactors that the production, the scale of production is not that much. The capital cost, the operational cost are very significant, right? So with that burden, now we're making a carbon that in many cases it varies. You need to understand very well to make a product out of that. And that is a significant challenge. And plus, we're competing in many cases with, for example, coal that doesn't cost much. If you're making, for example, biochar, and then you're going to be doing some activation, we're going to turn it into a filtration media. Well, people use coal that costs $20 a ton, right? So again, what we're trying to do is a system that makes cheaper material or low-cost material, call it like that. And also, we know what we're doing, and we're making it in an industrial scale, okay? But all these reactors, my opinion is that they're a little bit too expensive to make a profitable product out of this. And these are mobile reactors from different companies. This is Biochar Engineering. This is Agritherm. There's a few of them, okay? And I'm familiar with some of the owners of these companies. And then, well, with all that, this was like 8 years ago, we started with Arctic. And then a group of students from Iowa State, and putting things together and getting together over the weekends. And between beers, right? Always beers and conversations, welding and cutting and everything, being safe, right? So this is the concept that we have been developing all these years. And in the industrial system, I'm going to talk a little bit about this, and then Mateo is going to continue. But what we're trying to do is a modular system. You bring the material in a truck, it loads, it grinds, it dries, and then it pyrolyzes, and then it cools, and then you have your biochar. Okay, everything fairly simple. And with that being said, I'm going to let Mateo, our greatest engineers from Ecuador, by the way, is from your university. And he's going to be talking about the engineering side of Arctic. So, Mateo, go ahead. The field is all yours.
Excellent. Hello with everybody. Sorry, I didn't want to interrupt earlier. So, yeah, that's why I'm joining right now. Okay, let me, here it is. So we had a lot of information from Bernardo to understand how to produce biochar. And now what I want to talk about is, how in ARI we develop systems. Here it is. Okay, let me know if you can see the screen right now.
Excellent. I was going to tell you that.
Okay.
Not yet.
There you go.
Wait a couple of seconds.
Yep.
Okay.
We get it.
So how we are trying to develop a system with all this information that Bernardo told us. Of course, he already knew, and he started developing the systems. And like what do we need to do to handle the material? What are some important things that we need to know to have a good pyrolysis? Okay, so let me show you this. The equipment, our equipment, the equipment that we develop is the reactor. Okay, that is here, right here on the right side. And with the reactor, we produce the biochar. Okay, we have there 2 tons of biochar per day. So we produce, what we do is with a screw auger, we pass the biomass and we start heating it up and producing pyrolytic gases from the reaction. And then with that heat, we start cooking the material and producing biochar. We can vary the temperatures, and guess what? We produce a lot of excess heat there. Here in the flare, and in the flare, we use that heat to feed our dryer. And I'm going to explain a bit. I'm just giving you an overview of this. So from the beginning, we get the biomass. We need a way to handle that biomass, get into the reactor, grind it, We need to grind it to have a good particle size so heat transfer is good, and then get rid of moisture, okay? And then pass it to the reactor. And then at the end, we have the cooling tower here. It is to cool the biochar to 40 degrees Celsius or so we can handle it after. And it is also to stop the reaction, okay? Because otherwise we put it in, in storage and it keeps reacting, and we can have a fire that is a big problem. Okay. So here, for example, what I explained you before, we start cooking the material and we start producing gases, okay, in the chambers. And what I want you to understand is that the reactor is self-sustained. So once we start producing gases, we heat them up and it start the combustion process, and then it goes to the flare, okay, because you start cooking the material and you start producing emissions that we need to control that too. And one way of controlling that is producing a good combustion, and that is in the flare. Yeah. Here's another study that we have done in Arctic here, and that is the pyrolytic gases velocity inside of the reactor. And why is this important? There are a couple of reasons. We need, as I showed you before, it's self-sustained, and it self-sustains with the pyrolytic gases being combusted, and we need to have a good draft in the flare, okay? And when that happens, we start having some elutriation problems, and that is particles escaping the main tube where the material is cooked, right? And yeah, we want to control that, minimize elutriation. For example, this is what we do. We simulate a scenario to know how to design the reactor, okay? Let me show you another thing. For emissions, we have the afterburner from, so it is important that we have good emissions, that our reactor can can reduce the emissions, mostly because of the regulations, right? I mean, our objective is to be friendly environment, okay? And also, there are some cases where our clients, for example, needs to meet some standards and regulations, okay? And this is how we control that and how we help them achieve.
Mateo, can you just make sure that the audience understood about the gases? Why don't you show them the combustion chamber over there in that picture? You know, the particles coming in, getting cooked, getting pyrolyzed, the gases coming out, the primary combustion going on, the combustion chamber, and where the gases go.
Excellent. So you see here we have the biomass bin, okay? So here we put the biomass enters the reactor and it starts cooking, okay? So in this end, in the left end, we have the biochar being produced, and the pyrolytic gases goes to the back, right? So this is the flare. Let me see, maybe I can go to the picture at the beginning. Perfect. Okay, so this is it. So the pyrolytic gases goes to the back and the biochar goes to the front, right? And ends up here in the cooling tower. So here are where the first combustion occurs, in these chambers right here, okay? And then the secondary combustion occurs right here in the flare. Well, you see here, this doesn't have the afterburner, but we put it on top. And let me go back to the other picture. This is the afterburner, just so you know. And what we do is we heat up the gases, okay? And we control also the temperature of those gases. And how we do that? Well, first you need to have a good insulated system. You need to control
let's call it proprietary. So what we do is we control the amount of air that comes into the system.
Exactly.
Okay.
Exactly, and that is the point. Control the amount of air that goes into the system. And that is how you control the VOCs and the tetrahydrocarbons and make sure that you're having a good combustion before it goes to the flare.
Excellent. And just for regulations, so people understand, when you're going to be producing VOC. VOCs is volatile organic compounds. Pretty much, let's call it smoke, right? When you start the equipment, when you have a very tricky material, you can, for example, with little amount of energy, we cannot get the right temperatures, blah, blah, blah. Or when you turn it off the machine. So in those scenarios, they ask us to put an afterburner. So there's some VOCs being produced in some smoke that if you don't have this one, it will come out, right? So what we're doing in that black box on top there is we assisted with propane to get the temperatures of around 800, 850 degrees Celsius for a residence time of those gases of approximately 1 second, right?
Exactly.
When you do that, all the organics breaks down into CO2 and water. So that is the afterburner purpose. Go ahead, Mateo.
Yeah, and here are some simulations so you can see that you have here the trajectory of the particles going through the afterburner to the flare. And of course, the objective here is what Bernardo said, a residence time of between 1 and 2 seconds and a temperature of 800 degrees Celsius. And that will achieve the total, well, almost full combustion of those gases, and we'll be good. Yep.
And I think we should mention who was the owner of all that, who did all that, right?
Yes, that is Juan Sebastián Proaño.
Okay, excellent. Go ahead.
Here's another example of how we engineer the reactor, our equipment. So let me show you this. Here, there's an example of a screw auger. And sometimes we use, depending on feedstock, what we call mixer taps. You see here in the edge of the flighting. The flighting is the helix that goes around the shaft. We use mixer taps to mix the material inside of the reactor and also to increase heat transfer. From my experience, this is, well, it helps with heat transfer, and depending on how you assemble it, it will help you or not, because it can change the throughput of the equipment. Okay, throughput means how much material goes through the equipment, and that is because you see, for example, here we have a linear behavior of the auger, and just telling you an experience, what happened is that after we put the mixers in the auger right here, the material started to, go up and down instead of going forward, and that changed our throughput. So, yeah, that will help us to learn. And here is, you see the throughput over time, instant rate of throughput. Okay, so you can understand what I'm telling you. We have here, for example, around 50 pounds an hour at the beginning. The objective is to maintain a constant throughput here, and for this case, it was out holes, just so you know. And yeah, what was happening is that we got the throughput in half. Okay, so that is how we evaluate our systems and make them better.
Yes, and let me interrupt 1 second just so the audience understand. So in some materials, you need to mix it better so you can get a better quality of the material, better heat transfer, because sometimes, the particles on the outside just moves along the pipe and the particles on the inside gets uncooked, putting more in familiar terms. So in this scenario, what we're showing is how you can mix it, how you can move it, all this, and get a better quality. But at the same time, you got other challenges. Like in this case, we're reducing the throughput very significantly, almost to half of that. So this is some of the examples of those advances that we do to improve, in this case, the mixing, but also impacting the throughput as well. Go ahead.
Yeah. So just to clarify everything that I'm telling you right now, we have the biomass. I mean, we're trying to have a system that can process any kind of biomass, okay? And what happens is, yes, we have a new type of feedstock, we process it in our machine, and we have all of these challenges to solve. And we learn also from these challenges. And it is pretty interesting. So what I'm showing you is that how what we've been managing to overcome these challenges and also learn from them. So another thing, remember the flare that I showed you before here. After the combustion is done, we have a lot of excess heat right here. And we need, well, one way of making our systems more efficient is using that excess heat in another application. And here we have the dryer, the biomass dryer, and why it is important. Because, for example, imagine we have a 50% moisture biomass, okay? And the idea is that almost all of our feedstocks have water, a high water content. Well, not all of them, but most of them. And this means that if that biomass enters the reactor with a high moisture content, then it won't pyrolyze and temperatures will be low. And that is why we need to use a dryer so we can get that moisture out and then have a really good and efficient pyrolysis process in our reactor. Of course, the idea is not to have pyrolysis in the dryer. Yep, but just so you know.
And Mateo, just to give some numbers to the audience, especially the engineers, in our system, we produce a lot of heat, a lot of heat. Some of that it's being used in the pyrolysis, you know, but it's not much. And there's a lot more heat being produced that is actually, we have like the, let's call it the secondary combustion inside of that flare. And well, with that, we're using some of that to dry. Okay, but there's a lot more heat that we can use in process heat for any other application. Just so you guys have an idea, roughly that flare, it's 5 million BTU hour of heat constantly being thrown, and approximately 5 to 10% of that heat, it's used, obviously depends on the moisture, in the dryer. But there's plenty of heat, and we're trying to make a system that actually is versatile, and you can use all this heat for any other application, and certainly use it for drying the biomass. So you can make more material, the throughput increases, and well, you can process anything, which is one of our major challenges in the biochar world, is getting cheap material that you can process. And the moisture, it always comes with biomass, and you know, they come hand in hand. Go ahead, Mateo.
Perfect. So if we are using 10 to 20% of the heat being rejected from the pyrolysis reactor, that means we can still use that heat in other applications. And that is another characteristic of our system, that we use that heat, for example, in heat exchangers. And, you know, this is how we develop the heat exchangers. Yeah, let me show you this. So here, for example, this is a coil heat exchanger, and there's a lot of numbers, but the take-home numbers are this one: the inlet and, sorry, perfect, the outlet. So we start varying the design, and you know, trying to use that waste heat in good manners. This is just an example. Okay, so you can heat up water, for example, and this is another variation. So you see what is the problem here, that you have all of these hot gases coming out from the reactor and going into the flare, and you don't want to change the draft because you want to have good combustion, and then you want to have good heat transfer, and you have a lot of constraints. So you need to explore how you're going to do it. And these are some options that we have explored. For example, you see here, this was a cone heat exchanger, and this is how the hot gases, you know, it gets cooled down by the coil inside. Of course, it has water going through it, okay? And then it gets heated up. And here you have another configuration, for example, that doesn't changes the flow of gases inside of the flare, that it is important to maintain, okay? We do have other applications that are, for example, in greenhouses. Again, that is a heat exchanger. So you have a lot of heat that you can use.
Yeah, and these are just examples of how to use the heat, Mateo. And we can use it directly or indirectly, but the same. We're trying to make the system more economically, profitable, right? Awesome.
Perfect. And just so you know, these things vary from application to application. It depends on mostly what the people who wants the reactor needs. Okay, so on that it will depend if we use direct or indirect heat, or what kind of material we use, or yeah, all those things. And here's the cooling tower. This is the equipment that cools down the biochar, and this is how we have been improving the system and making it more efficient. And also this applies to our dryer too. That is a heat exchanger, and it works really good. So you have the base scenario here where you have no fins, right? This would be the vessel where the biomass goes through. And then you start adding fins. And we explore, we like to explore various scenarios. Here you have, for example, longitudinal fins, and this one would be a flying fin, okay? So the idea is to use the most that we can, cause the best heat transfer. And you see here we have exactly that, the results, and also get the desired outlet temperature, okay? So just so you know, some of the work that we do at RE, and how we approach, and how I approach as a mechanical engineer, these problems, after all the information, types of biomass, the amount of heat that you would need to evaporate the water, the amount of heat that you would need to cook the material, and also how much heat you are producing when you do that, and how you can use that excess heat in other applications. And to me, that is great. You have lots of things to work on. And yep, I think that is all I can share from the engineering side for the moment.
Mateo, you know what? We forgot to show them the video. Why don't we do this? Show them the video of the reactor running, and then we start getting some questions. And also in that slide that you were in, we have another video with just for fun,
Okay, let me
that we can
check
show
for
them.
the
But
video.
Juan, say if you can start sending us some of the questions, we can start addressing those and show them some other pictures that we have for the end of this presentation.
Okay, thank you very much, guys. Awesome presentation. It's really incredible to see how a small idea, like Bernie was saying at the beginning, how a small idea, few friends just having some beers and sharing some ideas turn into such a huge success. And a lot of opportunities for engineers and a lot of opportunities for farmers to develop these options here. So awesome, thank you. I think, I don't know if you prefer sharing your questions directly to Bernie or Mateo. I'm talking to you, the audience. Perhaps if you prefer to do that in English or Spanish, it's fine. So I'm going to open the mic for you guys to ask your questions. So now everybody can open their mic. And for instance, I'm going to invite Diego Mejia asking your questions. Either English or Spanish is fine.
And Mateo, why don't you show the video and then you do that, Juan? So
okay, let's do that.
Go, Mateo. This is a system, and talk about the components so people understand.
Okay, so here you see that, for example, that is the control panel. Here we have this would be the biochar transfer program where the biochar comes out.
Yeah, and this one we were adding water to cool it down. We weren't using, the cooling tower. And by the way, the cooling tower, we make them both with water and air. But in this case, it's added water.
Here is that would be the infeed auger where you put the biomass in. And then we are going to go inside of the reactor. There you can see all of the heat that is being produced there. That is because of the flare. So we grind the material, it goes into the dryer that has a lot of heat right now because the reactor is up to temperature. And then at the end, you have the biomass, the dry biomass going inside of the reactor. That is the flare. All of the gases being combusted.
And just to clarify, on the right, you could see the pyrolysis reactor. And from the very beginning of that pyrolysis reactor until, it depends on how you run it, but 5-6 feet up in the flare, all that is under fire. Okay, all that is just fire. Go ahead. Oh, there were some more slides that we passed, didn't we?
I am not sure, I think so. Oop.
All right. Okay, Juan, why don't you go ahead and open the mic for questions, and then we start showing some other slides.
Okay, thank you guys. So yeah, so Yegor, go ahead.
And you can do it in Spanish if you want, whatever you feel comfortable with.
¿Qué tal? ¿Cómo están? Buen día. Mi pregunta básicamente es el tiempo de producción de la energía que nos va a brindar el biochar, ¿cuánto es en promedio? Desde que se lo obtiene hasta el momento de consumo ya para el usuario.
A ver, hacémela de vuelta la pregunta.
En tiempo, ¿cuánto me demora en obtener la energía por biochar desde su producción hasta su consumo? Ok,
mira, el tiempo de residencia, yo creo que es para ahí donde va tu pregunta. En ese reactor, como estamos manejando ahí en ese video, es aproximadamente 15 minutos. ¿Ok? Ahí, en términos energéticos, en el biochar queda energía, pero será, no sé, 30-40% de la energía queda en el biochar. El resto se van los gases y en los gases, bueno, la combustión y todos los usos que uno tiene de la energía. Eso te diría números muy generales, ¿ok? Y espero no estar errado, pero eso sería un balance energético medio grande.
Listo, gracias, Bernardo.
Gracias. Mateo, why don't you show, now before we get to the next question, we're going to show one other slide. And this one, or move this one, but kind of quickly, it's 5 minutes, so jump. It's just to show, in this video, what we're showing is biochar here is used as an ingredient. I thought it was like 5% of weight, like 10% of volume of that soil. That is a very small pot. And we're growing corn and a soybean, and then I added fertilizer and I killed the soybean. But anyway, it was just for fun. It's just to show how you can grow a plant. Oh, you pass it too much. No worries. So you grow a plant. You don't need soil today to grow a plant, right? But the point is, if you put the biochar into that soil, that small pot, now it can sustain a whole plant growing by itself. Okay. Excellent. There's someone there that needs to mute. But it's just that. It's just to show, the capacity of growing stuff with biochar and the absorption of nutrient and absorption of water, which is very, very significant. That's a lapse time that I can show you guys afterwards, later if you're interested.
Okay.
All right. Next question. The next brave person, jump in.
Yeah, jump in, guys. English or Spanish is fine.
Yo tengo una pregunta. Me presento, soy Edgar Andrés Narváez. Soy ahorita presidente de RAI, compañero y amigo de Juan Sebastián Proaño. Yo tengo una pregunta. Habías mencionado igual que los gases de combustión pueden ser usados también como energía para poder calentar, por ejemplo, agua o incluso para algunos procesos dentro de la producción de biochar. Quería saber si de repente hay algún otro medio o algún otro proceso en el cual se pueda utilizar esa energía específicamente para la producción de biochar, en este caso.
Mateo.
Bueno, a ver, para la producción de biochar, ahorita los principales usos que le estamos dando a esa energía es para secar la biomasa. Entonces, solo para que sepas, manejamos lo que sería el concepto de un tren de pirólisis, ¿ya? Eso es lo que tiene el reactor que tuviste. Entonces, cada tren de pirólisis te va a producir gases que luego van a ser combustionados en las cámaras y luego en el flare, ¿no es cierto? Entonces, una manera bueno, la manera en la que utilizamos los gases en realidad es para cocinar la biomasa y que sea un proceso que se sostiene solo, ¿no? Y luego el calor que queda eh, lo utilizamos para secar la biomasa antes de que entre en el reactor.
Claro, para
Sí,
quitarle la humedad más o menos, me imagino, ¿verdad?
Claro, para que pierda la humedad y más puedas aprovechar la energía. En vez de evaporar el agua, la aprovechas ya directamente para pirolizar la biomasa.
Exacto. Y aparte de este proceso, ¿para qué otros usos se le podría dar? No para el proceso de la producción de biochar, sino, como habías dicho, para calentar agua también se puede usar. Tal vez
Claro,
existe algún otro, otro
sí,
proceso, ¿me entiendes?
verás, te doy como les dije antes, puedes usar para no sé, un greenhouse, ¿ya? Puedes calentar, mantener la temperatura del greenhouse, controlar, puedes calentar agua, puedes también utilizarla para, por ejemplo, un intercambiador de calor para alimentar un generador eléctrico. Bueno, y me imagino que hay otros usos directos ya del gas en sí, ¿no es cierto?
correcto.
A esas
Eso
temperaturas.
es lo que iba a comentar. Nosotros no lo hacemos, pero lo que Mateo estaba haciendo referencia es usamos el calor, ¿no? El calor que se produce porque tenemos que asegurarnos que todos los gases se combustionan completamente. Entonces el calor exceso lo usás para una aplicación u otra. Hay otros sistemas que lo hacemos en el laboratorio, pero no hacemos en los reactores grandes nuestros, donde sacamos los gases y usamos esos gases directamente en un motor o en lo que quieras usarlo. Pero son sistemas un poco más complicados, ¿no? Y de vuelta, nosotros nos estamos enfocando en la parte de biochar, y el resto vendría a ser coproductos. Por eso nos enfocamos más. Y para hacer biochar, todos esos gases hay que quemarlos se produce un montón de calor, usémoslos en forma directa e indirecta. Ahora estamos haciendo unos proyectos muy lindos con unas empresas que usan secadoras. Entonces, la idea es mover todo este calor usando, para esas secadoras que usan un montón de propano hoy en día. Pero hay un montón de usos, como decía ahora Mateo. Bueno, los heat exchangers que mostró en un momento era para agua caliente para un shop y que no se precisaba mucho, y eso va en el radiant heat, en el floor. También se utiliza los gases directamente, por ejemplo, en una greenhouse, ¿no? Uno saca los gases de combustión que está caliente, entonces calienta el greenhouse, pero también ingresa un montón de CO2 y otras cosas que para las plantas les sirven. Es decir, hay un montón de coproductos que se puede hacer a partir de estos sistemas.
See,
Listo.
guys,
Muchas
I'm
gracias.
going to interrupt you now. Bernie and Mateo, I want you to meet Daniela Almeida. She's the director of the chemical engineering department here in Universidad San Francisco de Quito. I guess she's got a question.
Excellent. Estás en mute.
Perfecto, gracias.
Dale.
Muchísimas gracias, Juanse, por la presentación. I don't know if you want to talk in English or Spanish, but I think we can
Either.
do Spanish. Excelente presentación, muchísimas gracias. Gracias, Juanse, por organizarla y por compartirnos este conocimiento. Yo tenía unas preguntas con respecto al diseño del reactor, no me quedó claro en la imagen. Entonces, ustedes están utilizando reactores Auger con tornillos. ¿Y para el calentamiento o para la reacción? ¿En cuál lo usan descendente? Uno están usando descendente y no lo están usando ascendente, ¿no es cierto? Porque le veo que tienen una pequeña pendiente. Entonces no me
Mira,
quedó claro cómo estaba diseñado y por qué.
perfecto. Mira, el ascendente es una secadora y
Ya.
y el otro que está casi horizontal, es el reactor. Pero
Claro,
son
supongo que un poquito
tornillos,
de pendiente sí les ayuda
sí,
para justamente evitar reflujo de material, ¿no?
exacto,
Y volátiles.
exacto.
¿Y cómo manejan los bitúmenes? ¿No tienen problemas con generación de bioils que se queden en el char o que se queden en los tornillos?
Excelente. No porque ponemos aire para quemar, y esos son los mismos biooils que nos dan el fuego. Entonces, los quemamos. Exactamente.
Bueno, y haciendo referencia a la pregunta del chico que la preguntó antes, claro, los gases y los bioils también pueden ser de muchísimo valor agregado, ¿no? Entonces,
Claro,
sí se podría pensar, no sé si es que han analizado los gases, si es que los utilizan para combustión, entonces quiere decir que probablemente tiene gas de síntesis y metano y
claro,
tanto. Entonces,
exacto.
se puede
Hemos
hacer una
hecho,
biorefinería después, ¿no?
por
Sí.
supuesto,
Conceptos de precursores químicos.
hemos hecho análisis de nuestros biooil que producimos y los gases de síntesis, exactamente, Daniela. El problema es que son sistemas mucho más complicados que les podemos mostrar también, pero
Sí.
es difícil para una presentación así explicarle biochar, biooil y los gases. Entonces, todo eso son nos enfocamos más en el biochar, pero todo lo que estás diciendo lo hacemos en el laboratorio y hemos medido un montón de nuestros gases, ¿ok? Pero en general no nos enfocamos mucho porque no es que haya un mercado tan grande para desarrollar eso. Los clientes que tenemos nosotros son todos de biochar y eso genera
Agricultura, ¿no
bastante,
es cierto?
claro, claro, claro. Agricultura y filtros, ¿eh? Filtros de aire, filtros de agua, la parte agrícola y unos clientes muy interesantes que tenemos en la parte de plásticos, porque hacemos un carbon black replacement que es muy bueno, muy barato y en muchas aplicaciones anda muy bien.
Ah, muy interesante. Muy interesante.
Bueno, bonito y barato.
Exacto, súper bien. ¿Y no han pensado, Juan, si ya tienes que traernos un equipo para ponerlo nosotros aquí?
Claro, ya
Necesitamos
tenemos que
uno en
traerlo uno.
Ecuador.
Sí.
Claro, por supuesto. Después de esta reunión nos sentamos a hablar con Juan, no hay problema. En la valija lo
Muchísimas
llevamos
gracias, un
cuando te
gusto.
vaya a visitar, ¿eh?
Unos 20
Eso,
viajes.
por
Che,
pedacitos.
Guys, okay, so now thank you very much, Danny, for your question and
Gracias a
Bernie
ustedes.
for your responses. Now let's move on. I think Valeria Bedoya had a question. Please go ahead, Valeria.
Oh, hi. ¿Puedo hacer la pregunta en español?
sí, sí,
Claro.
sí.
Sí,
Ah,
claro.
ya, bueno. Te quería preguntar si me puedes ayudar con cuál es la relación del CO2 liberado por la combustión
Sí,
y con el CO2 capturado en el proceso.
exacto.
Porfa.
No, perfecto. Aproximadamente, vamos a hablar de carbono, ¿no? Es solo la molécula de carbono. Aproximadamente el 50% del carbono se mantiene en el biochar. Aproximadamente. Con eso ya puedes hacer las relaciones luego, ¿no? 50% se va a ir en el flue gas.
Listo, gracias.
Buenísimo. Y Mateo, mostrá una de las fotos que tenemos al final, que son como los comodines. Está esto y Juan anda preparando otra pregunta. Esto acá es una foto del oxisol de las Amazonas, que ustedes, bueno, tendrán ahí terra preta, no sé, pero en Brasil hay mucho de esto. Son regiones muy chiquitas donde los indios cultivaban y ese es el mismo suelo, no sé, 100 metros aparte de lo que eran aquellos polos indios y los que eran los oxisoles nativos, es decir, sin alteración por los indios. Por eso pusimos The History of Biochar, The Oldest New. ¿Okay? Ahora otra pregunta, Juan.
Okay, guys, thanks. I don't have any questions on the chat room. Let me check on YouTube. They might have something there.
Bueno, Mateo, pone otro ahí, otro slide. Y
Yes,
acá
yeah, okay. Okay, go ahead, Mateo.
Change is coming and it's looking green, Artie. It's kind of catchy, I like that one. Bueno, pero ahí lo que estamos haciendo es agregando materia orgánica en los suelos y secuestrando carbono. ¿Okay? Eso es uno de los take-home message para tener. Juan, decime.
It's basically the same question as Valeria, so it's fine.
Okay.
But I have a question now regarding your products, guys.
Yeah.
What is the most popular one? What are they using it for?
Excellent.
And what is the trending future for those?
Fantastic. So we sell biochar products as is, and the biochar itself, it's the major product from us. And we're doing some other soil amendments. but the most popular is biochar. People buy from us biochar, but I want to sell them biochar products in warm casting, and the liquid char I think is a fantastic product that we launched it a little bit ago, and we need to market it and sell it because it's ground particles of biochar. And then, the efficiency of the product is a lot better now because it's, instead of one big particle, it's trillions of small particles holding all these nutrients and water and interacting with the soil in any level. So if you ask me, we need to push forward more and more the liquid solutions, and also the warm casting or the compost and biochar. Those are fantastic products, and people don't know I sell them those. People that know biochar, I sell them biochar. But as I was telling you before, guys, you need to know the basics of this, because, for example, you grab biochar and you put way too much biochar just coming out from the reactor. It's going to go into the soil and it's going to start absorbing all sorts of nutrients and water as well, right? So it will going to hold all these nutrients for a couple of weeks until it's stabilized with the soil. And guess what's going to happen with the plant? It's going to suffer nutrient deficiencies, and very significant. So that's why, in general, when I try to sell the biochar, we sell it, with all these nutrients and with all these microbes ready to be used. And now we don't call it, it's a biochar, but it's inoculated biochar with all this ready to use, okay? It's not just biochar straight out from the reactor, which is the product that we sell the most currently for people that are more familiar with biochar.
Awesome, thank you guys. So I think we ran out of questions from the audience.
Fantastic.
I don't know if Edgar has something extra to ask. Or...
Well, to ask, I don't have anything to say, actually.
Excellent. Well, Juan, thank you very much for the invitation, and thank you for being part of RD, right? And we all been developing this for a long time. We have a great relationship with the University of you guys, San Francisco, and well, hopefully we can keep developing this. And Juan, pass along your colleagues, but we make different materials. We can work with students in projects and keep developing this. And who knows, maybe in the near future we get a grant and we put a machine there and we start doing all sorts of internships there. My point is, we're open to develop of new projects and new products. So feel free to reach me, okay? And thank you for the invitation, guys.
Thank you very much, guys. Thank you, Mateo, as well. Actually, Mateo is alumni. So yeah, he can tell you about how we develop all these ideas and how he ended up working with Bernie as well in Mari. And yeah, we'll think about putting some grants together, and we can bring one of those reactors here to Ecuador. That has been an ambition for some time, but we need the funds, right?
Yeah.
Okay, thank you very much, guys. Edgar, perhaps you have something to add?
Yes, well, actually, I just wanted to say thank you to Bernardo del Campo and Mateo Dávalos for the presentation, for the conference. I guess we had a lot of participants here in Mexico that are from Mexico, Ecuador, and Argentina, I think. So it's good to know that people care about these things, and it's nice to try to inform the students of several parts of the world about what's the new advances of biochar.
Excellent.
Excellent. Thank you very much, guys. And for the audience, don't forget we have the last talk for next week. We have Professor Howard Shapiro. You know that guy, Bernie, right?
Yeah.
And you remember him. And he's awesome, and he's going to share his talk regarding exergy and industry. So
excellent.
We're looking forward to have you here with us, and enjoy the rest of the weekend, guys. Take care. And
Thank you very much.
Bye-bye.
Gracias, Juanse. Chao.
Chao, Dani. Chao a todos. Cuídense.
Chao.